Okay, looking at rates of change and the average rates of change, what we're going to do is we're going to come back to our friend, the difference quotient, and we're going to take a look at how that works with rates of change, because what happens is we can take quadratic functions or nonlinear graphs, and we can, at every single point on that graph, we could figure out what the rate of change is. Just by taking the interval, if we make the interval really small, then we can really look at it so that it actually looks like a straight line. So for instance, if we look at this graph here, and if I change the interval, or the window of this graph, so if I change it, instead of from -10 to 10, if I change it to be from 0 to 0.1, and look at the graph, it now looks like a straight line, right? And how do we find the slope or the rate of change of a straight line? All right. Well, if it's horizontal, it's 0, but we do change of y over change of x, right? So if I changed it to, let's see, let's pick another value. Let's go from 0.7 to 0.8. Oh, I got to change something else here. Hold on. Window from 0 to 1 to 2. Oops. 0.7 and 0 to 2. All right. Oh, okay. It's a little bit there. But what I can do is I can take it and so that it's so small, and let me try one more here. Let's go 1.5 to 1.6. But this still looks like pretty much like a straight line, right? And I can find the slope of a line by doing change of y over change of x. And one of the purposes for using the difference quotient, which when you get into calculus, is that we'll make intervals so small that it looks like it's a straight line. So when I do the derivative, what's called the derivative, or the rate of change, I can do it just by choosing 2 points, and it'll always work for you. So let's take a look at average rate of change first of all. And so we know that the average rate of change then, if I take 2 y values and 2 x values, find the change in them, then I can find the rate of change. So we're going to look at this problem here that involves when a rock is dropped from a high place. The distance the rock travels, ignoring wind resistance, is given by this function. And they have all these points given certain time frames. So if we want to find the distance the rock falls from time 1 to time 3, we can just subtract them, right? Put 1 in for t and 3 in for t, and then subtract those numbers. So it falls 128 feet from 1 second to 3 seconds. Well, question is then, well, what is the average rate of change during that time? And the average rate of change is we just take the distance they've traveled divided by the time it takes to get there, right? Okay. When you're looking at speed is like a rate of change, correct? Yes or no? Okay. So we're going to look at using the formula then that uses change in distance divided by change in time. So our average speed will be calculated by doing the amount of distance traveled divided by the time interval, which when we formulate it, it looks like this. Average speed is distance traveled divided by time interval, which means that we'll take the distance from our second value minus the distance from the first one over the time from the second one minus the first one. Right? Nothing new that we use for just finding slope. Okay? Change in y over change of x. change in distance over change in time. So for part A then, from 2 to 5 seconds, you should have found that it's 112 feet per second. At 5 seconds, it had traveled 400 feet. At 2 seconds, 64. So I take 400 minus 64 and divide by 5 minus 2. From 0 to 3.5 seconds, it would average 56 feet per second during that time. Distance traveled after 3.5 seconds minus distance traveled after 0 seconds divided by 3.5 minus 0. So we're going to focus on average rate of change, which is similar to average speed, which is still just basically finding a slope. Change in y over change of x. So this average speed is also the formula used for finding the average rate of change. So when they ask you for average rate of change, you're just doing change in y divided by change in x. Okay. And they put it this way, change in f of x, which is change in y, over change in x. And it doesn't matter what the function is, you can use it. In this case here, you can actually put these numbers in your y equals and use them. Okay? And I'm going to show you a little, I'll show you a little trick for doing some of it too. Okay. So here we have a cone-shaped tank is being filled with water. Approximate volume of water in the tank in cubic meters is given by that function, where x is the height of the water in the tank. Find the average rate of change of the volume of water as the height increases from 1 to 3 meters. So you can take your calculator, so we can use our fraction bar here to help us out. And so we're going to do from 1 to 3 meters. So we have 3 cubed divided by 4. Oh, except I don't want it there, do I? All right, so be careful with that. Yeah, that's all right. Okay, 3 cubed divided by 4 minus 1 cubed divided by 4. Okay, there's my numerator, right? Okay, let me help you out. So what we're doing is we're doing v with smiley faces. Okay. V of 3 minus v of 1 divided by 3 minus 1, right? Okay. So that's 3 cubed divided by 4 minus 1 cubed divided by 4 over 3 minus 1. Okay. All right. Now, this is easy enough to do without your calculator too, right? Okay. But I could do it here. Okay. I can do a fraction, and I can actually do a fraction there also. So I could do 3 cubed over 4 minus, and then put another fraction here, 1 cubed over 4, and that's over 3 minus 1. So doing it by hand without the calculator then, we have 27 over 4 minus 1 over 4 divided by 2. So we get 26 over 4 divided by 2. And this is like 2 over 1, right? Okay. So if we're dividing by a fraction, we're going to, okay, copy, change, and flip. So we're going to multiply by 1/2. So we get 26 over 8, which when I reduce that to 13 over 4. And what is this change? What's happening here? We need units. So what kind of units do we have? It's close to cubic meters, okay? But it's a rate of change. So something has to be, you have to have this is changing as this is changing. Okay? So we're talking about volume, right? Volume is changing as the height is changing. What's the volume in? Volume is in what? Cubic meters. Okay? So the volume is changing and the height is in what? Meters. So this is actually kind of a different form, but it's so 13 over 4 cubic meters per meter. So the volume, the cubic meters is changing for every meter. So it's like 3.25 cubic meters per meter. So as the volume increases by a meter, or as the height increases by a meter, the volume's getting that much more. But you could put those, what I'm saying is you could put those in your calculator too. You don't have to, but you could. Right? Manufacturing company makes toy cars. Cost in dollars of producing X cars is given by the function C of X equals the cube root of 4x squared plus 8. Find the average rate of change of the cost. So from 0 to 10 cars means I do C of 10 minus C of 0 divided by 10 minus 0, which would produce about 74 cents per car. Rate of change. But all these are is finding change in Y over change in X. Okay? Average rate of change. All we're doing is plugging in the two numbers they give us into our function, subtracting them, and then dividing them by the two numbers we're using. C of 0. Okay, I'm subtracting when I put 0 in. When I put 0 in, I get negative 8. Okay. And you could do this then. We could take and put this in our Y equals. Right, here's another. The cube root of 4x squared plus 8. And let's see, I could go by 5s in my table then, couldn't I? Because of the numbers I'm using here. Or you could do this. Go to your table setup, and you could go to ask. And when it's in ask mode, that means then you put in the numbers you want for x. So I want from 0 and I want 10. So there's my two numbers that I could use. For B, well, I've got 10 there. I just need 25. I could plug in 25. I'd find that number. And then I need 50. Okay? So there's my numbers to be able to find all of them. Okay? You could also, if you graphed it, you could hit trace, type in 0, we get 8, type in 10, 15.368, put in 25, and it won't give you a number. Why not? Okay, all right, it's not on there. I didn't go far enough horizontally. I would need to change my X max to go to at least 50 because I'm going up to 50 here. And then I could, and we'll change our Y also, 30. So I could trace, there's 0, there's 10, 25, and 50 also. So there's a couple different ways you could go about finding those numbers. Okay. So when we do that here, you'd find approximately 41 cents a car, and from 25 to 50, it's changing at a rate of about 32 cents a car. And the numbers we're using, so the numbers in the numerator are what I get when I put those specific numbers into the formula. The numbers in the denominator are just those two specific numbers. Make sure you always take the largest x and subtract the smaller x. Yep. You're finding these numbers 0, 10, 25, and 50, those are just your x values. And what's in the numerator is the y value you get from those x values. So if you just put them in if you just put the function in your y equals, it works really well that way. Okay. Yes, gallery. Can the rate of change be negative? Yes, it can be. When would it be negative? When? No. No. When it's decreasing, okay? In this graph here, it's always increasing, right? So it's going to be positive. But if we went into the negative values, okay, obviously they're not going to make negative cars, okay? But if we went to the negative values here, it's going down, so it has a negative slope. Average rate of change is just like slope. Line's going up, it's positive. It goes down, it's negative. All right. Was this picture on your paper? Okay. All right. So using a graph, sometimes using a graph is a little bit harder just because you have to make estimates, right? And when you're estimating, obviously they're not going to be, everybody's is not going to be the same, but they should be very close. So here they want from week 2 to week 4 on these. We've got the weeks on here for X, and we're doing sales on our Y-axis. And so they want to find out what's the average change in sales from week 2 to week 4. So I go to week 2, which is shown right here. At week 2 looks really close to 15. At week 4, it's about 12. So we'll take 12 minus 15, right? And divide 4 minus 2. Except this is in, oops, I don't want that one, hundreds of dollars. So you need to make sure you involve hundreds there. So from week 2 to week 4, they're losing $150 a week because their sales went down. It's never a good thing.
We're not losing, they just lost that much. Like they're still making money, but they're not, right?
Right, they're not making as much. Thank you. Yep. It's their average rate of change. Not making as much. So then from week 6 to 11, week 6 is here. It's approximately 1,400. Week 11 is here at approximately 2,200. So we find those changes, and we get approximately, it's increased in approximately $160 a week. right, so we have geometric interpretation of average rate of change. They use what's called a secant line. Okay. A secant line is just a line that's going to connect 2 points by a straight line. Right. Lots of times it's in different places. But the whole point of what we're doing here is still the same. We're finding average rate of change using those functions still the same way. This is still finding the change in y over the change in x. But we're going to use a little bit about the difference quotient though. All right. So the difference quotient, average rates of change, are often computed for very small intervals, such as the rate from 4 to 4.01, or from 4 to 4.001, really small intervals. Both cases are essentially the same, computing the rate of change over the interval from 4 to 4 plus h for some small quantity of h. It is often possible to define a formula to determine the average rate for all possible values of h. All right, so we're going to use the difference quotient here for this problem. So we've got 4.9 t squared is our function. So we're going to do the difference quotient. What's the difference quotient look like, first of all? Anybody remember? F of x plus h minus f of x divided by h. Now think about this for a second. Okay. We start at a value x. Okay. We've increased that value by h, right? That's all that means, x plus h. Okay. Now notice in the denominator, if I use that same thought process that we're using, that means we would have x plus h would be our larger value, right? Larger x value minus x, our smaller value. Well, what happens if I simplify what's in the denominator? What do we get? Okay. We just get h. Okay. So if you think about it, all the difference quotient is that function, that rate of change. Here I'm going from x to x plus h. So I do f of x plus h minus f of x. And then when I divide by x plus h minus x, we just get h. So this average rate of change here, all that is the difference quotient. It's the same thing. Okay. So let's see how we can use it. Ooh, got it all down there too, the explanation. So if we put 4.9 times x plus h, we're going to use x instead of t, squared minus 4.9x divided by h. There's our difference quotient for this function. No, you got to simplify it. Okay. So this is 4.9 times x squared plus 2xh plus h squared. We've done that a lot. That perfect square trinomial. squared. Sorry. So we get 4.9x squared plus 9.8xh plus 4.9h squared minus 4.9x squared. Yeah, that is exactly right. Okay, so these cancel. All right, the original function always cancels, right? The difference quotient. So I've been talking about the difference quotient. No, that was like a couple weeks ago, yeah. Yep. Okay, so we cancel out the h's, and we have 9.8x plus 4.9h. So here's what we do then. We're going to put the starting number in for x and the difference in for h. Okay, yep. All right. So it says they want us to find the average speed from 2.8 to 3 seconds. So I'm going to put 2.8 in for x and the difference in for h. What's the difference between 2.8 and 3? 0.2. And I'll put 0.2 in here. Okay. And somebody tell me what that equals. I could, but I don't feel like it. That would strain me a little bit. What? From 2.8 to 3. Okay, what's this equal? 26 point. What is it? 28.42. Okay? This is our average rate of change. Now, so if you take and do 4.9 t squared, put in 3, okay? Subtract 4.9 t squared, put in 2.8, okay? Subtract and divide, you get the same thing. So we can actually use the difference quotient to be able to find those values. 28.42 what? What are we doing here? Distance in meters over time per second. So this is meters per second. Thank you. I'm probably not. I'm probably not better than Miss Smallberg. Okay. Okay. So the average rate of change can be found by using the difference quotient also. And for number 6, if we use the difference quotient, it would look like this. Okay. All right. This was number 6 then. And I know how to cube x plus h, and so I did.